Our knowledge of Uranus's atmosphere is quite limited. We know it has a very strong set of winds that blows around the planet at about 900 kilometers per hour. But sometimes massive storms appear out of nowhere. These storms can last for years with speeds reaching over 900 kilometers per hour, even though there isn't any apparent trigger or source of energy to fuel them. And this doesn't make sense because Uranus is really far from the Sun. So, what could be causing these violent storms? Could they have something to do with the planet's core? I'm a presenter from a science channel, and in this episode, we're going to explore the possible causes of the sudden storms on Uranus. Uranus is sideways in the sky compared to Earth. If you were standing on its equator, you would see almost all of the sun's light coming from one side, while the other side is plunged into darkness. This unusual tilt might play a part in the giant storms that occasionally appear on the planet. But before we get into how these storms form, let us talk about the measurements we've taken of Uranus to see if we can figure out what could be causing them. In 1986, Voyager flew by Uranus and took some incredible photos of the planet. The most striking feature was the incredible cloud formations that looked like gigantic boils on the surface. But as far as we can tell, these boils are not actually boiling. They're not hot spots. In fact, the average temperature of Uranus is a frigid minus 224 degrees Celsius. That's way too cold to support the kind of convection currents that cause boiling. These features turned out to be storm systems that are thousands of kilometers wide and hundreds of meters tall. Some of them have been raging for decades. We also learned from Voyager 2 that Uranus's atmosphere is mostly hydrogen and helium, just like Jupiter and Neptune. There's probably methane and some nitrogen as well, which creates the beautiful blue-green color that Uranus is famous for. The swings in atmospheric pressure and temperature are thought to cause the hydrogen and helium to become supercritical fluids, which means that they behave like both liquids and gases at the same time. These properties are similar to what we see on Saturn, except Saturn's atmosphere has enough internal heat to produce a powerful jet stream that blows around the planet at more than 1,800 kilometers per hour. But on Uranus, the atmosphere is so far from the Sun that it's receiving very little energy. Scientists think that only 1% of the heat produced by the planet comes from leftover heat given off when Uranus formed. So, where does the rest of the heat come from? One theory is that the heat is generated by the planet's core. Scientists believe that Uranus is an ice giant, which means that its core could be made out of rock and ice instead of metallic iron. The swings in pressure and temperature in Uranus's atmosphere likely cause some of the compounds in the ice giant's core to break down into lighter elements like hydrogen and helium, releasing a tremendous amount of energy in the process. It's possible that this energy powers the storms that we see on the surface. But another possibility is that the energy is released through a process called nuclear decay, which involves the breakdown of radioactive elements like uranium and thorium into lighter elements. Either way, it seems plausible that the energy powering Uranus's storms is coming from deep within the planet. But why do these storms suddenly appear? Well, imagine heating a pot of water on a stove. You turn the burner on, and after a few minutes, the water starts boiling furiously. But if you take the pot off the stove, the water will eventually stop boiling. The same thing happens with the storms on Uranus. They gain momentum until there isn't anything left to accelerate them, and then they slow down and dissipate. Take the European storm that appeared in 1993, for example. For the first few years, the storm gained speed until it reached 900 kilometers per hour. Then it began to weaken until it was barely noticeable by 2007. Another storm that appeared in 2004 was fueled by the planet's internal heat and only dissipated after 10 years. These storms don't seem to last forever, but they are still quite long-lived. So what makes them go away? Is there some kind of feedback mechanism that stops them from gathering too much momentum? Well, the answer might lie in Uranus's interior. The swings in temperature and pressure as materials transition from being liquid to gas are enormous. This is called a phase change, and it releases huge amounts of latent heat. This process is responsible for many of the extreme weather events on Earth, like hurricanes and thunderstorms. For example, when air rises rapidly during a thunderstorm, it expands and cools, forming clouds of tiny water droplets. As the air continues to rise, the water droplets freeze into ice crystals that fall as hail. But if the conditions are right, some of the water vapor in the air condenses into liquid water, releasing heat and strengthening the updraft. A similar process may be happening on Uranus. As the gases in Uranus's atmosphere expand, they cool and form clouds of methane ice crystals. As the gases continue to expand, the methane ice crystals condense into a liquid, releasing heat and strengthening the flow of gases. Eventually, the process runs out of energy and the storm dissipates. To test this idea, scientists ran simulations of a storm on Uranus. They found that storms on Uranus grow until a balance is reached between the energy coming from the planet's interior and the energy lost as heat. This means that the storms aren't growing forever. They will eventually reach a stable state. Scientists are also looking into the role that Uranus's magnetic field plays in its storms. The magnetic field is offset from the planet's rotational axis by about 60 degrees. This misalignment causes the charged particles in Uranus's upper atmosphere to interact with the magnetic field in unique ways, generating electric currents that form powerful magnetic vortices. These vortices pull energy from the planet's interior, possibly helping to fuel the storms. Another factor that could be influencing Uranus's storms is its rings. The rings themselves don't generate much heat, but they do reflect a lot of sunlight. It's possible that the rings are influencing the way that heat is distributed around the planet, which could be affecting the formation of storms. Unfortunately, we don't have much data on this topic because the only flybys we've had were during the winter in Uranus's northern hemisphere. To learn more, we'll need to wait until NASA's Dragonfly mission reaches the planet in the 2030s. Dragonfly will take measurements during the summer in Uranus's southern hemisphere, when the storms are most active. The results of this mission could help us understand why these storms are happening in the first place. It is possible that we're witnessing convection currents in the atmosphere that we can't see because they reach too deep. Scientists can measure the depth of Uranus's atmosphere by looking at how fast the winds blow. Winds blowing at high speeds indicate that they're deeper and more powerful. By studying how fast the winds blow on Uranus, scientists hope to learn more about the structure of the planet's atmosphere. They've already discovered that the atmosphere is much deeper than they expected, thanks to the fact that the storms can rage for decades. These discoveries have led scientists to hypothesize that Uranus has a deep convection current that we can't see because it is hidden beneath the clouds. Convection currents are driven by differences in temperature and pressure. When there's a difference in temperature and pressure between two areas, heat will flow from the hotter area to the colder area until the temperature and pressure are equal. The same thing happens with convection currents in a pot of water on a stove. The water near the stove gets hot and less dense, so it rises while the cooler, denser water sinks. This cycle of rising and sinking water creates convection currents. Scientists think something similar is happening on Uranus. The heat coming from the planet's interior creates convection currents in the atmosphere, but the currents are so deep that we can't see them. Instead, we're seeing the effects of these currents on the surface, like the storms. The reason that these storms last for so long is because the convection current is very deep and it is taking a long time for the energy to dissipate. It's possible that the storms are triggered by small changes in the convection current, like a shift in temperature or pressure. These changes could be caused by the planet's rotation, its magnetic field, or its rings. Once the storm is triggered, it takes a long time for the energy to dissipate. This is why the storms can last for years. Scientists are still working to understand the role that these factors play in triggering storms on Uranus, but it's clear that the planet's internal heat is playing a major role. Even though Uranus is so far from the Sun, it's still emitting more heat than it receives from the Sun. Where is all that heat coming from? The answer could help us understand not only Uranus, but also other ice giants like Neptune and the hypothetical planet 9. If you enjoyed this video, you can check out my other videos. All the sources used are added in the description below. Thanks for watching.